Like I said before, if your array factor is just the sum of the weights times e to the j, k, d, n cosine theta, and you want that to be equal to 1 plus z to the big N minus 1, times some constant weight factor, you can just write down what the amplitude coefficients would be on here by multiplying out that polynomial. So if your total number of elements well, I'm going to skip the n equals 1 case because that's kind of trivial, but let's say we have number 2. Then our polynomial is 1 plus z to the big N minus 1, so that is 2 minus 1, which means that is equal to 1 plus z, and our weights are 1 and 1. If we choose n equals 3, that's 1 plus z to the 3 minus 1, or 2, which is equal to 1 plus 2z plus z squared. So our weights are 1, 2, and 1. Do n equals 4. 1 plus z to the 4 minus 1. 1 plus 3z plus 3z squared plus z cubed. So then our weights are 1, 3, 3, and 1. Not too bad. And those are actually the W sub n values. So if we wanted to put this array factor together, we would just have to choose our element positions. Let's say we had 4 of them, and put those W values on them. So we have 1, 3, 3, and 1 on there. And you can still steer them in the same way as you can steer a uniform linear array. So if you wanted the main beam to point, let's say at, 30 degrees off broadside, you could swap out z for some value of z prime, where that z prime is e to the j k d cosine theta minus cosine of the steer angle. Totally allowed to do that. Now, this is not the same notation that your book uses for the binomial excitation. I explained it this way because this way seems more intuitive to me physically, and it's easier to map the element weights onto the coefficients of the polynomial. The way your book writes it out is a little bit more mathematically efficient, but it's a little bit less clear. So now I'm going to convert what I wrote into the notation your book uses so that you won't be confused when you look at what's in the chapter. The thing is that the book numbers the elements differently so that they're symmetric about the origin. So if this is our z-axis, unfortunately I already used z for the polynomial variable, but whatever. Our element positions are going to be like this. And we're going to give them weights A1, A2, all the way up through A sub m. And we're going to assume that the array is symmetric. So we also have A1, A2, all the way through A sub m on the other side. Obviously, this is for an array with an even number of elements. If you want to have an array with an odd number of elements, you can do it the same way. You just put the two index 1 elements right here on top of each other. So you make that 2A1 like that. And then you number it all the way up through m plus 1. And then your total number of elements works out to be 2m plus 1 for an odd number of elements in the array. Then your array factor is equal to, if you have an even number of elements, the sum from n equals 1 to m, a sub n cosine of 2n minus 1 times u, where u is kd over 2 cosine theta. And if it's odd, then you have 2m plus 1 total elements for an odd number. And then you have the sum from n equals 1 to big M plus 1, a sub n times cosine of 2n minus 1 times u. And here, since then you have to say that the center element has amplitude 2 times a sub 1. This formulation works out the same as the one that I wrote down without the cosines. So the exponential formulation and the cosine formulation give you the same values of a sub n, except when a sub n, except when you have an odd total number of elements. In which case, the coefficient that you have, let's say like 2m plus 1 being equal to 3, means that you need the coefficients 1, 2, 1. In your equation, you are going to write down that a1 is equal to 1 because that element is getting counted double. And then a2 is equal to 1. But when you actually excite your array, you still only have 3 elements. So your excitation is a2, 2 times a1, a2. And those numbers have to be equal to 1, 2, 1. It's just a little bit convoluted to do it that way. But when we get to the Chebyshev polynomial version, it's going to make sense why we would want to write the array factor in that form. And I will do that in the next video.